These are my favorite, but I'm eating them for a reason. 1, I like them. And 2, this cookie has evidence of a chemical reaction. But what is a chemical reaction? Well, that is exactly what this program is about. Physical change in matter versus chemical change in matter. Our world is an amazing, ever-changing place. In order to make sense of the many changes we see in our everyday lives, like how these cookies changed from a bunch of ingredients to a delicious snack, we need to start with an understanding of basic chemistry. The first thing we need to know is that anything that has mass is called matter. Chemistry is the study of matter and how matter changes. How matter changes can be described as physical changes or chemical changes. The physical properties of matter are those things that can be observed without changing the matter or substance into another substance. Color, texture, shine, flexibility, and conductivity are all examples of physical properties of matter. When I crumble my peanut butter cookie, I have made a change to the physical property, but it is still a peanut butter cookie. Changing the state of matter is also a physical change. Freezing water to make ice cubes changes the state of water, but doesn't make new matter, so it's considered a physical change. Here's one more example of physical change. Maybe your mom or dad wants a cup of tea with their peanut butter cookie. If they add some sugar to their tea, the sugar will dissolve. Although the state of the sugar cube changed when it dissolved, the ions or molecules of the sugar could still come back together to form the original substance. This means that the change in the sugar was a physical change. Sometimes, matter undergoes chemical change. In order for a change to be considered chemical, the substance must change into another substance. Chemical changes are also called chemical reactions because of the process involved in changing one substance to another. The fender on my bike underwent a chemical reaction. My bike sat out in the rain too many times. So, over time, the water from rain and oxygen reacted with the iron on my fender. Unfortunately for me, a new substance, rust, was created. Let's review what we have learned so far. Question 1. What do we call the study of matter and how matter changes? A. Physics. B. Biology. C. Chemistry. D. Psychology. The correct answer is C. Chemistry is the study of matter and how it changes. Question 2. Which of the following is an example of a physical property of matter? A. Color. B. Texture. C. Conductivity. D. All of the above. If you answered D, you know that all of those are examples of physical properties. Here's question 3. What happens to substances when a chemical reaction occurs? A. They change their physical states. B. They change into another substance. C. They become more flexible. D. A and C. The correct answer is B. Chemical reaction is a process in which substances change into another substance. What are the parts of a chemical reaction? And how are chemical bonds affected by a chemical reaction? So, the rusty fender on my bike is an example of a chemical reaction. But not all chemical reactions are bad. In fact, without chemical reactions, many things in the world would not exist. Think about the sun, for example. It is the largest source of energy in our solar system. It is powered by a chemical reaction, the fusion of hydrogen into helium. Cooking and digesting food are examples of chemical reactions too. Each chemical reaction has two parts. Reactants are the substances that are used to bring about the chemical reactions. These are the ions and molecules that interact with each other and get the reaction started. Products are the atoms and molecules that are formed because of the chemical reaction. Let's look at my cookie. The reactants are the ingredients, like sugar, flour, eggs, baking powder, and peanut butter. The heat from the oven is a reactant too. The product is the delicious batch of cookies created by the chemical reaction of the ingredients with each other and heat. But how do chemical reactions happen? Well, chemical bonds are the centerpiece of chemical reactions. In order for a chemical reaction to take place, chemical bonds have to be broken in the atoms of the reactants. Once they are free and independent atoms, they form new sets of chemical bonds by rearranging themselves and then bonding together differently to form one or more new products or substances. These new products would have different characteristics than the original reactants. In my cookies, for example, the chemical bonds in the eggs, flour, and baking soda broke in the atoms as they combined with the heat to create the new product, my cookies. The chemical reaction that created my cookies happened pretty quickly. But it is important to remember that chemical reactions can occur at different rates. We just need to remember my rusty bike fender to see how reactions can happen quickly or slowly over time. After all, my bike's fender didn't get all rusty in one day. Instead, I forgot to put my bike in the garage several times, and it got rained on. The iron in the fender reacted with oxygen and water over a long period of time until the iron became oxidized into a new substance called iron oxide. The cookies that I eat and the bike I ride are really helping us understand chemical reactions. Let's review what we just learned. Question 1. What do we call substances that are used to bring about chemical reactions? A. Inhibitors. B. Accelerators. C. Reactants. D. Solutions. If you answered C, you know that reactants bring about chemical reactions. Here's question 2. What do we call the atoms and molecules that are formed as a result of chemical reactions? A. Products. B. Outcomes. C. Artifacts. D. None of the above. The correct answer is A. Products are the atoms and molecules that are made from chemical reactions. Question 3. What has to happen to the bonds between atoms and reactants in order for chemical reactions to take place? A. They have to be broken. B. They have to join together. C. They have to multiply. D. They have to create energy. The correct answer is A. Chemical bonds in reactants have to be broken. What are the changes in properties that occur as a result of chemical reactions? So, how do we know for sure that a chemical reaction took place as these cookies were baked? First, we have to remember that a change in physical state does not mean that a chemical reaction has taken place. Water frozen into ice doesn't make a new substance. It is still water. Mixing matter together doesn't create a chemical reaction either. Let's say the manufacturer had decided to make a batch of trail mix instead of cookies. The company would have mixed dried fruit, nuts, and chocolate chips together in a bowl. Sure, this makes a new mixture, but if we had the time, we could separate out all of the original ingredients because they had not undergone chemical change. So, what tells us that our cookies are a result of chemical change? Lucky for us, there are several observable signs of a chemical reaction. One common sign of a chemical reaction is a change in color. If the reactants are a different color than the product, it is likely that a chemical reaction has occurred. Our cookie batter was a yellow-brown color when it was in the mixing bowl, but after the batter came out of the oven, the cookies that were produced were a golden brown. Another sign of a chemical reaction is the emission of an odor. Or, does the product give off a smell? Well, ours sure did. That delicious baking cookie aroma made my house smell great. The production of a gas is another sign that a chemical reaction has taken place. The appearance of bubbles sometimes tells us that a gas has been produced. Think about how our cookies started out as a wet batter mixture and ended up as fluffy cookies. This happened because the heat of the oven caused some of our ingredients to release carbon dioxide gas. We know this because we can see tiny little holes when we break open our cookies. These holes tell us that the gas was released. One last sign that a chemical reaction has taken place is the production of a solid substance called a precipitate. A precipitate is formed when two or more liquid substances are put together, and a solid substance is formed as a result of their chemical reaction with each other. To get a good understanding of this idea, we sadly have to leave the aromatic example of our baking cookies and head to the bathroom. You know that soap scum that can accumulate in your bathtub? Well, that is an example of a precipitate. Soap scum forms when certain molecules in hard water react with soap materials. Soap scum is not just little bits of soap. It is a completely new substance. We know this because it doesn't bubble and dissolve easily like soap. As you can see, some chemical reactions are yummy and others are not. Let's review what we just learned about the signs of chemical reactions. Here's question 1. Which of the following is a sign that a chemical reaction has occurred? A. Change in color. B. Emission of odor. C. Production of a gas. D. All of the above. The correct answer is D. All of these are signs of a chemical reaction. Question 2. Which of the following is a sign that a gas has been produced? A. Bubbles. B. Rocks. C. Light. D. None of the above. If you answered A, you know that the presence of bubbles is an indication that a gas was produced. Question 3. What do we call a solid that forms as a result of a chemical reaction between two liquids? A. Mixture. B. Substance. C. Suspension. D. Precipitate. The correct answer is D. A precipitate is formed from a chemical reaction between two liquids. What changes in energy occur as a result of chemical reactions? We were able to see that my peanut butter cookies had some strong evidence that there were changes in the properties of their ingredients. But what about changes in energy that can occur as a result of chemical reactions? Remember that chemical reactions involve breaking bonds in reactants and forming new bonds in products. The breaking of bonds requires energy, and the releasing of bonds releases energy. So, as matter changes as a result of chemical reactions, it can either absorb or release energy. Chemical reactions that release energy to their surroundings are called exothermic reactions. In exothermic reactions, this energy is usually in the form of heat. Exothermic reactions, therefore, often produce an increase in temperature. The gas oven the manufacturer used in baking the cookies produced a chemical reaction that released heat into the oven. A bonfire is an example of an exothermic reaction too. The dry wood we use to create the fire has potential chemical energy. Once the wood is ignited, the potential chemical energy will be released and converted to heat energy and light energy. The wood from the fire turns into ash, which is a completely new substance. Not all exothermic reactions produce heat. Some produce light. The glow sticks we may use around a bonfire are a great example. One of the reactants in glow sticks is a solution of hydrogen peroxide, which is stored in a tube inside the plastic glow stick. The rest of the stick is filled with a second chemical and a brightly colored dye. When the stick is bent, the tube will be broken and the two solutions will mix. The result will be the bright glow of light. Some chemical reactions produce a decrease in temperature. These are called endothermic reactions. These reactions need to absorb heat from their surroundings to proceed. In fact, many endothermic reactions occur only when heat is constantly added. Like with the cookie dough for these cookies. It needed to constantly absorb heat in order for the cookies to bake. As the cookies absorbed heat, the oven temperature went down by a tiny amount. Not all endothermic reactions absorb energy as heat. Some absorb energy as light. Photosynthesis is an example of one of the most important series of light-absorbing endothermic reactions on Earth. Let's review what we have learned about changes of energy in chemical reactions. Question 1. What do we call chemical reactions that release energy to their surroundings? A. Biometric. B. Cellular. C. Exothermic. D. Endothermic. The correct answer is C. Exothermic reactions release energy. Here's question 2. What usually happens to temperature during an endothermic reaction? A. It decreases. B. It stabilizes. C. It increases. D. Temperature is not affected. If you answered A, you know that endothermic reactions often produce a decrease in temperature. Question 3. Photosynthesis is an example of what type of chemical reaction? A. Endothermic. B. Scientific. C. Exothermic. D. None of the above. The correct answer is A. Photosynthesis is a series of endothermic reactions. What is the conservation of matter? Believe it or not, there is an important scientific law behind these delicious cookies. It is the law of conservation of matter. This law states that during a chemical reaction, matter is neither created nor destroyed. The total mass of the reactants must equal the mass of the products. This means that when a chemical reaction happens, you can't create new atoms. You also can't destroy atoms as they are reacting. The atoms simply rearrange themselves into new substances. Remember our cup of tea from earlier? If we dissolve a sugar cube in tea, the new mass of the tea will equal the mass of the tea plus the mass of the sugar cube. It is easy to see the law in that example. But what about the law of conservation in our bonfire? Originally, many people did not accept the law of conservation of matter. They saw that when you burned an item, it would weigh less after the reaction took place. They did not realize that sometimes mass was lost through oxygen. A bonfire starts with a pile of logs. As the fire burns, the pile of logs will slowly shrink. By the end of the evening, a small pile of ashes is all that will be left. What will happen to the matter that we started with? Will it be destroyed by the fire? Although it may seem as though burning destroyed matter, the same amount exists after the fire as before. Here's why. When wood burns, it combines with oxygen and changes not only to ashes, but also to carbon dioxide and water vapor. These gases float off into the air, leaving behind just the ashes. Suppose we had measured the mass of the wood before it burned and the mass of the ashes after. And suppose we were able to measure the oxygen used by the fire and the gases produced by the fire. What would we find? The total mass of matter after the fire would be the same as the total mass of matter before the fire. Where did this idea of the conservation of matter come from? It was the ancient Greeks who first proposed the idea that the total amount of matter in the universe is constant. However, it was the French chemist Antoine Lavoisier who described the law of conservation of matter as a fundamental principle of physics in 1789. Thanks to Lavoisier, the scientific community now knows that gases are just another state of matter. From my cookies to a bonfire, chemical reactions are all around us. Let's review. Question 1. The law of conservation of matter states the total mass of the products of a chemical reaction must equal what? A. The total mass of hydrogen atoms. B. The total mass of the gases involved. C. The total mass of the reactants. D. A and B. The correct answer is C. The total mass of the reactants must equal the total mass of the products. Here's question 2. Who first proposed the idea that the total amount of matter in the universe is constant? A. Ancient Greeks. B. Ancient Romans. C. Ancient Egyptians. D. All of the above. The correct answer is A. The ancient Greeks were the first to propose that idea. Question 3. In what year did French chemist Antoine Lavoisier describe the law of conservation of matter? A. 1789. B. 1885. C. 1902. D. 1995. The correct answer is A. Lavoisier described the law of conservation of matter in 1789. Thinking question. Name a chemical reaction you see in your daily life. What evidence tells you that it is a chemical reaction?